All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we will begin. First off, good afternoon. I am Jason Thomas, Project Engineer at America Makes, and your host for today's America Makes TRX Webinar Series. A little background on the TRX Webinar Series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange Webinar Series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX Webinar Series, there will be a link to complete the request form at the end of our series today. Or you can contact the America Makes TRX Webinar Series Administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get all the questions answered. Today's webinar is on tips for choosing the right 3D printing material. It will cover the differences and trade-offs between 3D printing materials for stereolithography, selective laser sintering, PolyJet, multi-jet fusion, carbon DLS, and direct metal laser sintering. Key material properties for plastic and metal additively manufactured parts, and shortcuts to understanding which types of 3D printed materials you should pursue for your design. Without further ado, it is my pleasure to introduce our presenter, Amber Farmer from Proto Labs. Amber is an application engineer at Proto Labs with experience in additive manufacturing. Her focus is on stereolithography, selective laser sintering, multi-jet fusion, PolyJet, and direct metal laser sintering technologies, and provides guidance to engineers on designing for manufacturability. She graduated from North Carolina State University with a degree in chemistry and chemical engineering. Amber, I will now turn it over to you and your team.
Hey everybody, my name is Amber. Today I will be giving an overview of our 3D printing applications with the goal of helping you decide which is best for your application. Here at Proto Labs, we offer 6 3D printing technologies, liquid-based and powder-based. Stereolithography, carbon, and PolyJet are liquid-based. Selective laser sintering, multi-jet fusion, and direct metal laser sintering are powder-based. In this presentation, we will cover material offerings and common applications for all of our technologies listed here. We will start with our liquid-based technologies and move to our powder-based technologies. We will start with stereolithography. This is best for prototype iterations, form and fit testing, and cosmetic parts that require fine featured details. This slide shows general minimum feature requirements for stereolithography. We can generally form and clean holes as small as 20 thousandths of an inch in both normal and high resolution, and 10 thousandths of an inch in micro resolution. The minimum channel and gap requirements are also shown here. Form the smallest features in the XY plane, which is perpendicular to the direction. The minimum feature size in the Z is going to be higher, and it's a limitation of the technology, and it depends on the resolution. We can do 16 thousandths of an inch in normal and high resolution, and 8 thousandths of an inch in micro resolution. Within stereolithography, we offer ABS-like materials that are generally durable all-purpose materials with well-rounded mechanical properties. These materials also have relatively low moisture absorption, which is generally an issue with SLA. Our micro-resolution materials can form extremely small, precise features down to 2.5 thousandths of an inch, which is beneficial for highly precise medical device prototypes. The watershed material is capable of functional clarity through secondary finishing, which is useful for microfluidics and light pipes. Additional applications are electrical housings and snap fit assemblies. We will also describe more of functional clarity through custom finishing later on. Polyjet-like materials have a relatively high strength and stiffness. There are two high temperature materials, Accura 5530 and Somos Perform. Accura 60 is also capable of functional clarity. Common applications are medical device prototypes, high temperature applications, electrical housings, and lighting or light pipes. Our polypropylene-like material, Somos 9120, is our most flexible within stereolithography. However, the elongation at break is going to be slightly lower than the injection molded counterpart. Common applications are snap fits, medical device prototypes, electrical casings, and fluid flow analysis. There are a number of custom finishes we can offer. Clear finishing is one of the most common. This entails sanding the external layer lines to a very fine grit and applying a polyurethane clear coat. Common applications are microfluidics, diagnostic devices, and light pipes. The image on the left shows a full dress that we did for the Met Gala, and that shows off our custom finishing pretty well. These are other custom finishing capabilities that we can do in addition to clear part finishing, such as soft touch paint and color matching. We can also do decals and graphics and add texture through painting. Here are some more images of dresses and accessories that we made for the Met Gala. We can plate stereolithography with copper and or nickel. This is commonly used when durability and lightweighting are required. Common applications are handheld medical instrument prototypes, wire cutting guides, and fixtures. UVision 360 is one case study we would like to share. UVision 360 used our micro-resolution microfine material in stereolithography to print prototypes with very fine features. They were able to save about $250,000 in tooling revisions by finalizing designs of over 20 parts before ordering steel tooling. Carbon is our newest technology offering. It is best for low to mid-volume production projects with moderate aesthetic requirements and parts that are less than 5 inches long. We currently have two material offerings within Carbon, the flexible polyurethane FPU50 and a rigid polyurethane RPU70. RPU50 has good impact abrasion and fatigue resistance with moderate stiffness. RPU is strong with moderate heat resistance. Common applications for Carbon are medical prototypes and production parts, durable clips and connectors, hinges, and assembly components that cannot be machined or molded. This slide shows a comparison of Carbon to SLA. SLA is going to be able to form smaller features. It also has a smoother surface finish and better accuracy. Carbon has better material properties and it can be built faster. And it's so because of the better material properties, it's better for production parts. The PolyJet technology offers elastomeric materials ranging from 30A to 95A durometer, as well as a rigid material. Due to the material offerings, it is well suited for overmolds. Common applications are gaskets, overmolds, and prototyping for LSR. A Cool Idea award winner used PolyJet to prototypes for a medical device that allows doctors to clean patients' ears quickly. Due to the nature of the project, they needed to prototype customized components during the trial stage. This is where they used PolyJet and stereolithography to print components. Now moving to our powder-based technologies, selective laser sintering is best for functional testing and end-use plastic parts with moderate aesthetic requirements. These images are screenshots of the build prep process. The middle picture shows nesting of parts within the build box. The screenshot on the right-hand side shows the printing process where the laser sinters the powder. We offer both unfilled and filled nylons. Each nylon is best utilized for specific reasons. For example, PA11 black is best for flexibility and heat resistance, whereas a filled nylon is best for high stiffness and load-bearing requirements. Common applications are jigs and fixtures, housings, functional end-use parts as the nylon are production grade, gears and bearings, as well as snap fits. Another cool idea, award winner MedStar Health used SLS during prototyping to improve the design of their syringe holder for a gravity feeding system intended for feeding babies in the NICU. Multi-jet fusion, or MJF, is another technology that has a nylon material offering. It is best for prototyping production grade parts and geometries that are too complex for machining and molding. There are currently two materials in MJF, an unfilled and a glass-filled nylon 12. The benefit of using MJF over SLS is more isotropic properties and smaller feature resolution capability. Common applications are housings or enclosures, fixtures, snap fits, and living hinges are recommended in the unfilled nylon. OVR technology has utilized the mechanical properties of MJF for low volume production of their scent-emitting device prior to scaling for traditional manufacturing. They were able to distribute the devices to clinicians sooner than anticipated while still making design changes, which meant they didn't have to pay for tooling changes. Each technology has their own advantages. When comparing MJF to SLS, MJF will have a finer minimum feature resolution, 20 thousandths of an inch compared to 30 thousandths of an inch in SLS. It also builds faster and it has more isotropic properties and a little bit improved surface roughness. SLS is going to have a more consistent surface color. It can also be dyed multiple colors because most of the materials are white, so we can dye them, whereas MJF is black, so we're not able to dye it. If you are comparing the nylon material, MJF or SLS to carbon, the advantages of each technology are that SLS and MJF have generally lower cost and they don't require support structures, whereas carbon will have a smoother surface finish, smaller feature size, more variety of material properties, and more isotropic material properties. Direct metal laser sintering is best for combining multi-part assemblies and producing complex geometries and functional metal components. On the left is a list of our material offerings in metal. Common applications of DMLS are medical device prototypes and production parts, as well as custom fixtures and tooling. This slide shows some material key benefits. If you want strength, you would choose Inconel, titanium, or stainless steel. Whereas if you want temperature resistance, you would also choose Inconel or titanium. If you want lightweighting, you would choose aluminum, titanium. Each material has their own benefits. In DMLS, we can produce features as small as 6 thousandths of an inch in high resolution. Meshes are also possible when designed properly, which are shown in the middle picture. We can produce large parts in DMLS. We recently obtained a new printer that can produce metal parts as large as 31 inches in length. But however, this is only available in the Inconel material. The surface roughness of DMLS parts range from 200 to 400 microinches RA, and it is dependent upon the material, resolution, and orientation. Select surfaces can be machined or polished if a smoother surface finish is needed. Here's a list of our secondary operations. With a standard finish, support removal, followed by a grit blast, and bead blasting occurs. Upon request, we can perform machining. We have a full machine lab in DMLS, capable of milling, tapping, reaming, lathing, and EDM. All parts are stress relieved post-build and undergo quality inspection. Thank you so much for your time. On over to git.protolabs.com/3dp-selector. You can get a free 3D material selector. And
all right. I'm sorry. Thank you, Amber.
No.
We'll now head into the Q&A session. So if you have a question for our presenter, Amber, and you have not done so already, please type it into the question box or the chat. Either way is good. I'll start out with a question that we have here. So what additional resources do you have to learn more about 3D printing materials?
Yeah, so if you go to our website, we have some white papers, and that can be searched in the home page near the bottom of the screen. And that is where you can find additional resources.
Okay, great. So another question, what additive technology do you see on the horizon that could have an impact on the industry?
I know that carbon-filled materials